Now, as an introduction to the periodic table, it's important to realize that, yes, elements are classified in vertical columns throughout the table, as well as in horizontal rows throughout the table. And the placement is not coincidental. Elements are placed in these various rows and columns based essentially on their electron arrangements, what we call configurations, but more importantly, those configurations impart certain chemical properties to the element in question. So what we're really doing is we're going to focus our attention on placement of elements according to their chemical properties, these being properties that measure reactivity with other elements. How do atoms behave with other types of atoms? That's what chemical properties really measure. Now, first of all, we notice that we have 18 vertical columns in this periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Now, these vertical columns have a name. They're referred to as groups. But they're also sometimes referred to, and this is a more telling reference name, they're referred to as families. Now, family is a better name in some respects because a family is a group of relations, people who are related to each other. And of course, the families here on the periodic table are entire groups of atoms that are related by their chemical properties, how they behave with other atoms. For instance, if I were to see how lithium were to react with, say, nitrogen, I would notice that it forms compounds in a 3-to-1 ratio. For every 3 lithium atoms, we would get a nitrogen atom in our compound, and vice versa. And the same would be true of sodium. Sodium also reacts with nitrogen in a 3-to-1 ratio to form another compound, as does potassium, rubidium, and yes, hydrogen would, though we often write the compound that hydrogen forms with the nitrogen first, for a reason that will appear later on in the year. So yes, atoms of the same group tend to behave the same chemically with other atoms. And so, of course, if we talked about an atom in a different group then, say for instance, group 2, magnesium. Well, remember, sodium reacted with nitrogen in a ratio of 3-to-1, but magnesium's in a different group, so while it's related to the other members of its group in the same way, it's not going to be related to members of the adjacent family. So yes, in fact, magnesium does react with nitrogen in a different ratio to form compounds with a 3-to-2 ratio of the atoms. But so would calcium. Calcium would also do the same with nitrogen because, of course, they're in the same group. So that's why the term family is an appropriate name for these groups. Now, for the horizontal rows that we see throughout the periodic table, and there are in fact 7 of them, 1, 2, 3, 4, 5, 6, 7. And of course, these 2 rows down here are in fact part of the 6th and 7th row. If we could take this and squeeze it down and insert it right here, yes, elements 57 through 70 would appear right here, and elements 89 through 102 would be right in this part of the periodic table. But then the table would have to be drastically elongated, and of course the surface area would be greater, and we'd kill more trees to make paper periodic tables. So not a good idea at this point. In any event, these rows have names as well, and they're referred to as periods, and that's where the table gets its name, periodic table. Now, in science, the meaning of the word period is any regular repetitive pattern of events. For instance, if a pendulum is swinging back and forth, one complete cycle back and then forth would be the period of the pendulum. A wave vibrating, oscillating up and down One complete up and one complete down would be one period. The moon has a period as it revolves around the Earth. One complete rotation around our planet would be the period of the moon. Now, the regular repetitive pattern of events that we see in these rows of elements are why they are called periods, and here's why. If I choose, say, the third period and I look at group 1, I know that sodium will react with oxygen in a 2-to-1 ratio. On the other hand, the next member of the next group in that period behaves differently because it's in a different family. It reacts with oxygen in a 1-to-1 ratio. The third member of the group, if I skip right across to group 13, aluminum behaves differently still. It forms compounds with oxygen in a 3-to-2 ratio. Silicon, a 1-to-2 ratio, different than any I've seen thus far. Phosphorus, a 2-to-5 ratio. Sulfur, well, it all depends. There are many compounds of sulfur with oxygen, but the point being we can use just these to see why this is called a period. Because when we get to argon and drop down to number 19, we begin a new period. And of course, because potassium's in the same family and is related to sodium, it also reacts with oxygen in a 2-to-1 ratio. Calcium reacts in a 1-to-1 ratio. Gallium, 2-to-3 ratio, and so forth and so on. In other words, I'm seeing the same repetitive pattern of chemical property events. So a great name for these are periods. Now, as for general behaviors over broad-reaching groups of atoms, most periodic tables have a line that I sometimes refer to my students as the line of death that cordons off the right side of the periodic table from the overwhelming majority of elements found on the left side of the table. And yes, this is almost 3/4 of all the elements on the left side. These are all referred to generally as the metals. And those wacky chemists, of course, came up with a great name for the ones that aren't like the metals over here on the right side. They went with nonmetals. Talk about your technical naming system. Well, these two behave very differently in one very important respect. Namely, metals, in terms of chemical properties, tend to get oxidized when they react with other elements. In other words, they tend to lose electrons. They are the electron punks in the world. They give it up easily because they're too wimpy, they haven't had their Wheaties, they don't hang on. And we'll be discussing what makes these elements less inclined to hang on to their electrons. But of course, by their very nature, nonmetals must then have a much greater attraction for electrons. They're the bad boys. They're the ones that go around jacking everyone else's electrons. And yes, they tend to get reduced in most chemical processes when at all possible. So you have oxidation going on with the metals and reduction going on with the nonmetals. But also important is the elements that lie right along the line, namely boron and silicon and germanium and arsenic and antimony and tellurium and polonium. Oh, I wish I could sing the Tom Lehrer song of the elements. It's a great one. The only one not on this line, right here, aluminum, is definitely a metal. But all the rest that line this line are referred to as metalloids. And what makes a metalloid a metalloid? Well, it has both metal and non-metal behavior in some respects and properties. For instance, we know that metals tend to conduct electricity, allow electrons to freely pass through them. Whereas nonmetals, of course, that's because they get oxidized, they give up electrons. Nonmetals tend to hang on to electrons and get reduced, so electricity would not flow through nonmetals well. They're not good conductors of electricity. The wires in our house are made of metals, copper especially, but the outside of the wires are insulated with plastic, of carbon and hydrogen mainly, And of course that prevents the electric flow from going out of the wire and maintains it through the wire along the metal. So some of these elements have both behaviors depending on conditions. The metalloids are semiconductors, and yes, that's why the Silicon Valley, where silicon-based semiconductor chips are produced for computers, is called the Silicon Valley, though those chips also have a lot of germanium and arsenic in them as well, though the primary component would be the silicon. So yes, they have properties of both, and we're actually in transition along this line, going from metallic to non-metallic behavior, and they walk the fine line between the two. Now, of additional significance to us as chemists, we often use words instead of numbers to represent the groups. For instance, all group 1 elements, except for hydrogen. Hydrogen's the outlier. It behaves like them, but it's not a metal. It actually should live over here with the nonmetals, but because its chemical behavior is so much like the metals, it is nevertheless listed in the same column as these group 1 metals, and we often refer to them as the alkali metals. And the reason for that wording is because alkali implies basic, namely a solution that has basic character or quality, and if you throw any one of these elements into water, they'll react with the water and make it very basic. So that's how they got the name alkali metals. Now the group 2 metals also go by the name alkaline and often earth metals. And if you have trouble remembering which is which, I always use the mnemonic that alkali ends in an I, and an I looks an awful lot like a 1. And alkaline has 2 more letters, and we're talking about group 2 when we talk about alkaline earth metals. Another element that, or another group of elements, family, that has its own name, and a very important family is right over here. These guys are referred to as the halogens. Halogen. G-N-S. And lastly, but certainly not leastly, another group that is often called by a common name is this entire group of elements known as the noble gases. So you have your noble gases and your halogens and your alkaline earth metals and your alkali metals. Now, other general references, since everything to the left of this line is in fact a metal, these guys right here that are sort of in transition between groups 2 and 13 are often referred to as the transition metals. And then this bunch down here, which is also metals, are often called the rare earth metals. And in fact, they are rare. And some of them, as a matter of fact, are man-made. They don't occur naturally, and that makes them, of course, pretty rare. So these are some references where you can immediately tune your attention to a specific part of the periodic table if you hear them. If I were to say, well, what alkaline metal is in period 5? I go 1, 2, 3, 4, 5, and here's alkaline, must be talking about strontium. Or what is the halogen found in period 3? 1, 2, 3 halogens. I'm obviously talking about chlorine. So these are some of the particular references to the periodic table. Now, old school tables, they have numbers labeled 1, 2 for the first 2 groups. Then these are subgroups, and the labeling picks up with groups 3, 4, 5, 6, and 7, and 8 instead of 13, 14, 15, 16, 17, and 18. And if you have a periodic table that uses that numbering system, then these would be referred to as the main groups. So if I said main group 3, I'd look here at 13 and not there. So you can play in both worlds if you know this system.